So I think we will start now. I will shortly present now the use of mercury, just very simply, because as I said, it's very intuitive. This is our structure which we solved. And now you can see the presentation, what we so-called quartet presentation here. Now on here we have a managed style, it says quartet, and here it says ellipsoid. So you can see we have ellipsoidal presentation. And it is a very nice presentation of your molecule. But what you have to do often in this case, and this seems to be quite, and this is tricky, what happens, quite often the students, when I ask them to do it, they do it like this. And then they send this to me. Then this is my structure. Yes, of course it is your structure, but I can't see anything, what is there. So always when you're presenting your structure, rotate it in a position where you have a minimum overlap. So then it's very easy for everybody to see each individual atoms, like in here. And sometimes you can have a really complicated structure. So it's like I was showing yesterday, the spheres, the molecular spheres. There's always, because a three-dimensional object, whenever you turn it around, there's always something on the back. But if you have this kind of a simple molecule, then it's easy to do this. And the point in here is that we can here easily change the presentation style. This is the classical ball and stick presentation, where you have all the atoms are presented as balls. But this is of course not the real one. The previous one, when you have the ellipsoid, is the real one. But what I always want to show is here is so-called space fill. And this is the actual how the molecule really looks like. So it's really the idea that the real shape of your molecule, or if there's a hole or not a hole, can only be seen when you're using the space filling mode, the CPK, and now when you rotate this molecule, it looks in essence the same as it was, but it's much thicker, it's bigger. And this is actually the volume what this molecule takes in the crystal lattice. But I will show you now very briefly about the hydrogen bonding. I will go back to the ellipsoid presentation like this. And now, here in the lower part, there is a nice note which says, look, hydrogen bonds. And now it is looking, but now it's not doing anything more than just looking for what is the nearest acceptor atom. Because here is a donor. Now, this donor is hydrogen bond. But now in here, there's no problem. This is an acceptor. But now it thinks that there is now a molecule here, or atom, which could be the donor. But now, if you look carefully, you'll learn it later on, of course, we use here in the right-hand corner now, it says expand contacts. So when I go on top of this and click, it draws the next molecule. And if I go here, now it clicks this one. Now if I rotate this in this way, you can see that there's a chain. The molecules are bound to each other by this kind of a hydrogen bonded thing. So now we started seeing how the molecules are talking to each other. And this is of course what we have to know in many of the cases. We are looking, okay, where is the other molecule? How they are organized. And now this organization, it changes slightly, but the components are the same. Then we call it as a polymorph. It's the different structure from the same molecule. Different crystal structure. And they might be so that there might be 10 different crystal structures for the same molecule. Because they come from a different condition. Remember when we grow the crystals, we can change conditions. And now it might depend on the solvent system conditions, which kind of structure comes out, even from the same molecule. And pharmaceutical industry is very keen on this because you can patent new polymorph, even if it's known compound. if somebody has never found this polymer, you can patent it and use it in your drug. So that is quite interesting feature what crystallography has brought. But that's the case. But now I will go back a bit. I will say reset. Reset is a very nice process. It kills everything else and returns back. But now I will do another thing. I will now ask it to look for one hydrogen bond only. So let's take this one here. Sorry. This one now. And now, if I unclick this one, it doesn't show anything else than now this. It doesn't show the hydrogen bond anymore, but now we know that there's a hydrogen bond. But now there is another trick, because in real life, there is no, these doesn't exist. Of course, this is just a presentation. Like in here, there's no such a bond in here. This is only embedded, it's inside there. So this is just presentation. So in order to see this nicely, is to use the space filling for this. So we do this. And when I click space filling, now you see an interesting thing. I put it in this way. Like this, let's go up a bit. Now I will change it back. We have a better orientation. Now I'm trying to put it nice, like this. So now look this region. So there is the hydrogen bond is here. But it seems to be that the atoms are like floating very far away. But that's not the case, because when you click here, space fill, you see now that this hydrogen is now interacting, hydrogen bonding to this one. So when you're using the space filling, you can really see the bond. It's not just a number, you can see it visually. And this is how it goes. So now let's reset this thing, go back to the ellipsoid, and now what we can do easily, of course, now I will show you quickly. Let's measure distances. Here, I will move it a bit, we can move the labels. I can here. And now this is the same number which was there in the table, but sometimes it's better to show some features in the picture. So you can do it and keep it in there, and then you can take a print out of this. Okay? And there are just clear measurements. Yeah. The point is there that if I would like to see more what happens, so the other form is this, I can look for the interactions, but if I want to see the whole thing, where are the other atoms? That's the packing. And then the packing is actually, there is a knob here on the left-hand side, say packing, like this. And now, this is a typical mistake. In many of the forums you say that, okay, this is now a view along certain axes. So A axis or B axis or C axis. But if you now look carefully, it's not. This is not along any axis because it's like a sideways. So when you do this, you have to be careful, as you say, but in here there's a knob that says A. Now the view is along A axis. So we are looking, here is the origin and A, so we are looking from this direction. So when we are looking along A, we have a BC plane in this thing. So that would be the view of packing along A axis. And then if you ask, okay, what is the same thing along the B axis, you just go here and click this one, and that is the view along B axis. So the packing is different. And then of course you can look that also from the C axis, and then it looks like this. This is the worst view, because there you can see the other molecules are in front of the other ones. So it seems to be, in this case, the best would be, what happened? I lost my voice. I think so. Not my fact, but it should be okay.
No, battery could be the case.
It's now it's on, but it doesn't, so maybe it should stop. Maybe it's a battery. But I will keep it on as long. It could be battery running out from here. No, that's the idea. So that would be the nice view, but this is not very pleasing because now it's looking upwards. So what we can do, there's additional thing in here. We can go, in this case, say rotate set 90 degrees. And now we have a nice view. So we have an origin here and along A-axis. We have an AC plane towards looking. And that's the idea. That would be a very nice view of packing. But now this is also the idea when this is the normal way of showing these things. But this is not true. Because immediately you would ask, what is there? What is there on this side? There is a lot of empty space here. So can it be so that the atoms are floating in there? That is not actually true, and that's why it's always better to look these things, what you have, really on a space filling. And now you can see there is no empty space. So it's completely full. And to show it even better, that will be the last one we will move. I will go here and ask it a packing, but now I will ask it to calculate a bigger area. Now this is 4 unit cells. And now when I rotate this, now you can see that there is absolutely no empty space. So this is so-called closed packed structure. So all the molecules are packed like this. And now we have been talking about the cops and moths and all these porous materials. It means that then in the structure there will be a pore or a cavity or whatever. But in this structure there's not. So all the molecules packed in this way. And this is what we can do with these programs. We don't have time to go through and have a rehearsal or practice these instruments, but if you just download the program and you have the file, then you can play around with this. Or with your own, maybe now or in the future, if you're doing this kind of work, you can use this for that purpose. But now, let's now move to the final thing. Which might be scientifically more interesting, because these are the examples of the structures collected over that's lost that the I think we can take that one and then change the battery. There it is. This thing works. Okay. Then they are showing you examples of how or into which kind of resistance you can use, or we have used, single crystal X-ray diffraction. Remember, everything comes from the fact that you have to have the crystal. And once you get the crystal, then you have a high chance of getting the structure, even a very complicated structure. It looks, when you see it in paper, which said this will never crystallize, you will never get the structure. But I will show you examples. And these are now large supermolecular structures, some very complex ones, which have been obtained by single crystal X-ray diffraction. Just to remind you that, of course, before we get the structure, we have to have the crystal. And remember, the crystal is ordered system, so each of these dots now is our supramolecule. We have to be able to organize the supramolecules in the 3 dimensions, and it has to be a nice crystal of something like this or that. And this is the actual idea, I think, that what we can get out from there. I yesterday showed you only halogen bonding for these, but we have done all of these. It is that you can extract this information, like we did as an example. We were looking for the hydrogen bond. You can study everything in there. So the information of the X-ray structure, like my colleague told yesterday, you can find a lot of things inside the structure which can explain the behavior. For example, synthesis, other things. It can also, in some cases, also have an indication or hint to solid state properties, and all these kind of things. So the molecules pack in a certain way, they are photoactive, for example, all these kind of things. So that is the very important part. And these are all interactions which occur in the crystal structures, either between the molecules, like when they pack, or between the host and the guest molecule. So we have a big molecule and something goes in. So this is retrospective. As you can see, this is quite old stuff, what I did in there, and then it contains these more complex molecules like kryptons, catenanes, rotaxane, helicates, grids, tetrahedral cube, knot. As you can see, they are not called any particular name like ibuprofen or aspirin or whatever. So these are large assemblies which form themselves. So this is about supramolecular self-assembly, because you throw the components in there and then you isolate the assembly, and then if you're lucky enough to crystallize it and then get the structure. And this is actually how I started my career. So this work is my first with Jean-Marie Lehn from 1991. So we were doing this kind of kryptons because he was at that time still working with the kryptons. And then you can see it's a closed bicyclic structure, and it contains, in this case, 3 silver atoms. And it's there. And it's really now 30-something years old, 34 years old structure. And I did the structure in Jyväskylä for these guys. So it was a combination of the Mendoza, Fröckle, and Lehn. And then later on, I continued with Jean-Marie with helicates. So he was the person who actually developed double and triple helicates structures. And this is a really interesting structure, which is a double helicate, which make a cycle. So it's in certain sense it's 2 times the same thing.
Hold the microphone close.
Okay, like this. Okay, it's a cyclic structure, so it's a long one. So it starts from here, goes up there, and then on the other side it starts from here and goes up there. And this is how it looks. And now there's an anion inside. So it is a self-formed helical microcyclic structure by self-assembly. And this is also quite old stuff now. And the point, this is from the PNAS 2001, and one of the co-authors of this paper was, if he's not anymore, Romanian science minister. So he moved, he was Romanian, and he moved there. Then I did also some other catenane work. And we had an interesting thing. So there's a catenane. A catenane is 2 microcycles joined together with a mechanical bond. So it's like a magician strings. That's the catenane. And now here we have an X-ray structure of a very specific catenane. Here is the CPK model, because I always show it like this, because if you think, okay, there's a lot of empty space here, no, it's like this. But now you start seeing there's pi-pi interactions in here. CH pi is there. But the most interesting thing is here that there's an azo group in there. So there's a molecular break in this. So with light you can change this to cis or E conformation, and then the rotational freedom of the system changes. And that was also quite old, 1993, and it was actually published in an Angewandte journal just before Fraser-Stoddard published a very similar structure. And you know, Fraser-Stoddard got the Nobel Prize in these things. Fritz Fröckle was very close to, he was a very clever guy in doing these kind of things. Okay. Yeah, it works. Yeah, okay, that's fine. That, I'll go back. These catenanes. And remember, the instrumentation, what we had 25 years ago, is nothing what we have now. So these were rather complex things to be done, but the reason here why this was successful was the crystals. So we get big enough, good enough crystals that we can have this. And this is not considered a very complicated structure at all. This is one of the simple ones. But anyway, the catenanes is a very nice family of compounds. Then what we did also, I've done work rotaxanes. A rotaxane is a system where you have a microcycle and then you have an axle here. So there are 3 microcycles like this, and then there's a rod going through that. That's a rotaxane. Again, this thing comes by itself. So you mix the components in the solvent and wait, and then you will have this. So that is a rotaxane. And you can see here, this always gives you a slightly different opinion about this of you, but that is how it really looks. So it's really compact structure. So nature normally, especially in a solid state, doesn't like vacuum or empty space. So the molecules normally have to touch themselves, and that's what happens here. And there's pi-pi interactions within these. So we did quite a lot of work with Jean-Marie on his rotaxanes, but we also then later on, you can see 2007 or so, in the early 2000s, he was interested in grids, so molecular grids. So molecular grid is, it's like a moth, but actually it doesn't make a framework, so it's make a discrete molecule or complex. So the idea is like a grid, so there's 1, 2, 3, 4 atoms here, 4 ligands, 2 in this direction, 2 in that direction, you can see here. And this particular case, there are 2 different metals. So then you can do photochemistry or whatever, you can study how this changes in there. That was a really quite hot topic subject 20 years ago. And then we go to bigger systems. Now you can see molecular weight is 6,500. And this is now the construction. So you can, there's a porphyrin with the 4 pyridine rings in here, and then this kind of a curved system where you have a porphyrin, zinc porphyrin in there. And this work was done by Jean-Pierre Savage, who got the Nobel Prize then some years ago on the discovery of molecular machines. This is not the molecular machine, but this is a very nice example about that we can scale up. This work was done 2009, so nearly 20 years ago also. And this is how it looks like. It's very bad looking, but that is actually how it really looks. So here there is really a tiny hole here in this area. So here it's huge, but now you can see here that it's actually a very tiny one. But that's the case. So now we can have a structure on atomic resolution for this. But then the idea is that he sent me this. So it's a very impressive molecule. So it has 524 carbons, 52 nitrogens, 30 O atoms, 4 phosphorus, 24 fluorines, copper and zinc. And the molecular weight is about 9,000. So when you see this kind of a molecule, which has a long rod, you can see that, look how lipophilic this part here is, and that also, it has this kind of a thing, a huge structure like this, that no way you can do this. But I would of course not show it to you if that was not done. So actually we were able to do this with our in-house instrument. And now this is the X-ray structure of that. Here are the, here you can see, it's curved a bit in this direction. So in here too, and the zincs are there. And we could even see that there is a molecule attached to the zinc. Water molecule is attached to the zinc. So we get more information from this done, but that was really the idea. And why Jean-Pierre Savage was doing this, he was doing molecular press. So the actual idea is that these parts here are able to move around this. So they could trap molecules inside here. This is an empty one, but that's the case. And this is how it looks with the CPK. These are the pore anions, so it's a really huge structure. And this was published in 2008, and then 9 and 10. And these were the papers on this kind of rotaxanes. It's just a big thing to do. But now let's go to a little bit more, because I was showing you the structures before we get this kind of, because there were molecules. But now I will show you a couple of examples that when you do this thing, you know, quite probably don't know what you get. And then the analysis of what you get is very difficult, and you have to be very convincing. So let's make a tetrahedron. But let's make a tetrahedron that is not existing. So we take all the components needed for this, and the idea is that then we call this metal ion assisted self-assembly in water. And now this thing has 22 components. So 22 separate things are put in water simultaneously. So what happens? And you would easily consider that you would have a big mixture, get the polymers and all this kind of not clear stuff, but no. Really, it works like a clock, and this is what happens. So now, we take the spheres, these are the metal cations, what we need in there. Then we have two different types of ligands, organic ligands. So we have the green and the blue one. They are separate ligands. And now we put all of them simultaneously into water. Now, what happened? There will be metal ion assisted self-assembly, and even so that you can consider that these are subcomponents. So we don't have the ligand yet, but it will be formed by itself from these components. And self-assembly creates this. So now you can see that we need two of the green ones and one of the blue ones to make a one edge, and then we have the metals in the corners. That's the tetrahedron. Happens in water by itself in a quantitative view. So X-ray structure. Now why this was interesting was this. So this is now an image of not a metal, although it looks like a metal. This is P4. This is white phosphorus, and the white phosphorus is kept in water or underwater, because if you take it out, this happens. It starts to burn. So you have to keep white phosphorus in water that it doesn't burn. So it's the idea of what happens here now. The white phosphorus, which is P4, spontaneously ignites when it's out of water. When it gets dry, it burns. And now, you ask me why. Well, I will show you this. Remember what we did, or the nature did by itself. It made a tetrahedron. And now, what is the structure of a P4? It's not linear, and if we start thinking about this thing, it's tetrahedron. But it's a small one. So now, let's do this. So we did it. So when we did this and we put all these things simultaneously in a water which contains white phosphorus, the white phosphorus goes inside the cage. And now it's trapped inside there. We call it white phosphorus and is encapsulated in one. And you can see here what are the ligands. They're very simple ones. So pyridyl aldehyde and then this diamine with this kind of a sulfonate groups, and the P4 is there. And now in the water, if you have water, you put there benzene. The benzene will kick out the white phosphorus, and then benzene goes in. So we can exchange this thing. Of course, you will ask, why is this possible? Okay, here we have it in cartoon. So we have a pink solution of water where the white phosphorus is inside the cage. We put N-heptane, nothing happens. Because now the N-heptane cannot go into the cavity. It's like a bear, and this is a snake, so it doesn't want to go there. But now benzene is like another bear, a bigger one, which kicks out the white phosphorus, and now the white phosphorus comes out from the cage, and now the cage contains benzene, and that's there. And this is actually what we did, and this is now the X-ray structure. And the X-ray structure is really crucial, showing that the white phosphorus is inside. So it's here. Now you can see the rotating image. So it was rotating a bit. The idea that here is there. And here we have the white phosphorus, and I draw it with the space filling model, and you can see that it's really tightly trapped. And now remember that if you take white phosphorus by itself from water, it burns. This doesn't. So we had it in the table for 3 months, nothing happened. Because you can consider that it's like a fire, put it inside a bottle. So it doesn't do anything as long as it's in there, but immediately when you open it, it burns. And this happens also with this. So if you take this and you grind it, then you break the cage, it burns. And that was the science paper with this. And there is a colleague, President Ma, who is now in Tunasla. So we did the same thing. So we did the similar things. We had an idea that we can encapsulate white phosphorus, which is like a 4-atom tetrahedron. And can we encapsulate an atom, a single atom, inside there? And we work with the physics group in Finland, who are very famous on hyperpolarized xenon. And what we did in this, we trapped xenon inside the cage. Again, the same. These are the components, very simple, iron, and then in xenon gas was there, and this happened. We didn't have the X-ray structure of that. Unfortunately, we have a very nice NMR. We can see in NMR, okay, yes, here we have these cages where the xenon is encapsulated inside. So this is, and it happens by itself. So we continued the work ourselves. These are the similar cages, but now with the different guests. And here, the pointing there, and then we got a lot of X-ray structures. They're all different. So inside there, in each of them have a different guest. And now this is how it looks like from outside. So there is chloroform, dichloromethane, tetrachloromethane, and so on. Tetrachloromethane. We published this something like 10 years ago. And then there was a collaboration also with President Ma, also in this case vessels. Now, can we make something different? And can we get an X-ray structure? Okay, now we made their tetrahedron. Let's now make a cube. The cube needs 38 components. And now we are approaching the molecular weight of 10,000. As a single molecule, isolatable molecule. We have to make it and crystallize and then get the X-ray structure. And this is the synthesis. It's a very simple synthesis because you can buy the compounds. You can buy this. This is commercially available, and also this is the pyridyl aldehyde. You mix them up only with the iron 2 triflate in DMF. That's the intermediate, and that's the thing what happens. And now, X-ray structure is very important to show that is it really a cube with no windows. And there is the X-ray structure. So this is now one view, this is another view, and here we can see the CPK, or the, if you can see all, the space filling model. There is no windows. It's really a cube, really a box. But it's not, because it consists of metal cations in here, in the corners. It is a complex which can open and close. A little bit like what we had the idea, how can the tetrahedron trap the other small molecules? It has to open. So we did the study, or Nietzsche did the study with this, with hydrocarbon. Here you can see the X-ray structure of it. It's an empty inside. So if you take coronines, 3 coronines will go in. And then if you take your C70 and put the C70, the coronine will, these coronines in here, will kick out their C70, and then you bring it here. But if you have an empty case like this, when you put C70 there, it's C60 is there, it goes there. But now if you put C70, it also goes in there. But now in here, in this case, if you do put C70 in there, it kicks out C60. So it means that C60 is less happy inside the box. And if you put C70, C70 kicks it out. So it's like a football in a box with bounces around. And C70 is a bigger box. And unfortunately, we never get an X-ray structure of those, but that was shown by Anamar, Masbeck, and so on. But that was the X-ray structure of this one. And it was also done a little bit more than 10 years ago. And now, can we do an even complicated thing? That's the reason. Hopefully I will... my trousers will stay, hopefully, on. I need this for that. So the point there is that can we make a knot on a molecule? And then how the this is possible? Because you know that it's really difficult to control a molecule in a solution because it has a Brownian motion and it has all the possible conformations. So how in the heck can you make a knot? And even better, can you make a 5-fold knot? That it goes 5 times. So let's try this. And it's interesting, it only has 15 components, it's about 5,000 molecular weight, so it's rather large, but let's see how it goes. So we take a rod, they're all the same rod, but I keep different colors, you can understand what happens. Now I have then 5 other rods, which are the same. And then I need this times 5 balls, these are, of course, you can imagine, metal cations. So let's mix them as previously, let's see what happens. Nothing. Nothing happened. So we realized these were incorrect ones. So we have to change now the spheres, the metal cations to different one. So we change them, and this comes out by itself. So what is this? Now you can see the colors are here, the same colors, and then these are the connectors in the corners. And then there is something strange here in the middle. These wild balls seems to be like this. So what is this? This is a pentafoil knot, formed by itself. It's in the Moroccan flag, but you can also do it at home. This is the easiest way to do this. But it's the same thing. Now, the actual idea of the chemistry is very simple, or not. So you have to synthesize this, and then you have to take the connector point, which is this kind of a ethylene glycol-based diamine. Then you again have iron in there, and then later on you will do an anion exchange for this to get it crystalline. And this is actually the molecule. This is the knot. This is how it goes. It will be very complicated to see, but I will show you better that it is really a knot. So it's the idea is there, that the molecules go like on that. So that's how the X-ray structure looks like this. So you can see there is no empty space. So it's really a tight knot. And then in here is envelope. Now these are the same connections, but I deleted all the atoms which are not part of the chain. So let's start from here. So we are on the top, we go here in the loop, and then here it goes down. Then in here we go up, loop, down, up, loop, down, up, loop, down, up, loop, down, and up. Again. 15 nanometers long thing, which does this by itself. And the point in there is that this is how it looks. This is the X-ray structure of that. And then the other, we actually sent this to Science, but they said no, it's not interesting. And then we sent it to Nature Chemistry, and it was accepted in 120 minutes. So in 2 hours. Nearly instantly it was there. And then they wanted us to draw, they said that, okay, this is so nice that you can get a cover of Nature Chemistry for this. So we prepared a very nice looking picture of this kind of a thing, and that's the chloride which is sitting here inside there. And the idea is that they were not happy about this, but why this is so interesting, I will show you the idea is that what really happens there. So this is now the 150 atoms for 15 nanometer long thing. And then when I start doing this, you can see what happens. So 1, 2, 3, and then 4, and then I will close it like this. And now, this is our, okay, it's not that nice looking, but here we have our pentafoil knot. So you can see it was that long and it squeezes in like this. It's impossible to do it in any other way like this. So you assemble it, you build up that, and then you connect the corners for this, and then you can get this kind of thing. So we were very happy. Actually, I did one form, and they did also this kind of, but no, the journal said no, it's not good, so they made their own one. And this is now the cover of the Nature Chemistry. And here we have our knot is there, and then the chlorine is there, and then it says here, star is born. Because it looks like a star. And after that, they bleed it, a dark Star of David, and all these kind of things. Now, a little bit more, what we can do. So sometimes you face really big surprises. And this is a very interesting thing to show you what happens under the X-ray structure can tell you. So I got this kind of a structure. It's a microcyclic, relatively small amino acid based microcycle. And this is the person, this is Stefan Kubik from University of Kaiserslautern, Germany. And then this thing was there, you can see what is there. Is a phosphate, diphosphate in there, and it's crystallized from acetone. And look here, the mass of this compound, including everything, so these are four, because this is cations here, and this is this is neutral, so we have a salt in there, so it's a trigonal or ternary system. So the molecular weight of this should be 1,762, roughly. But now, what happened? So we found very nice, well-diffracting crystals, colorless plate, very good. Of this size, rather small, but this was decent, okay, and it gave a unit cell. Remember, we have to get the unit cell in order to get the structure solved. And now, the A is 22, B is 31, C is 61, and the angles are 70, 80, 70 something, so it's triclinic with a volume of 40,000. This is typically an indication that there is something wrong in a crystal. So it's not a single crystal, it's something else. That whatever is coming out from there is not true. But anyway, I decided, okay, let's try this and let's see what happens with this. And the idea is, why is this? Because if you calculate, remember this is the formula, what we saw earlier. So density equals the number of the units with the molecular weight divided by the Avogadro's number in Ohmströms and volume. Density, number, formula, units, and so on. Now we calculate. So we estimate that the density of this is 1.2, like an organic compound. This is now the Avogadro number. This is now the volume divided by 2, because in the triclinic system we should have 2 molecules in there. Then it says the molecular weight of the thing should be 14,000. How is this possible? How can it be? Because we have this which would be 1,700. How can it be 14,000? Something must be wrong. But the point in there is, now, it turned out to be that it was a very good crystal. I could solve the structure, and these are all the atoms which are there. So it was not one single molecule there. It was a big group of things. So what is this? This is actually a constitution of this type with a molecular weight of nearly 13,000. So our calculation was correct. So the molecular weight there in the asymmetric unit, so what we have to define is this 14,000 roughly. And what it actually is, it is a combination of 2 of the microcycles, 2 of the cations trapping 2 phosphates inside there. And then there are several of these. So it was really a complex structure, but we didn't have no clue about this, what it is. So here are the different presentations. The cations or the anions inside are blue, cation is green, and then the microcycle is red. And you can see it's really compact. It's really like this kind of package. And it has 2 components. And then there are more of these in there. So this is a different presentation showing now the anionic species inside the either the cation is there. Yeah. And this is so-called Hirschfeld surface, which tells you that there is a really strong interactions of the anionic species with the microcycle. So it traps it, but it cannot trap it 1-to-1. It traps it 2-to-2 fashion. And then the cations are blocking there. So in the lattice there were 4 of these capsular entities, TPA cations, and then the phosphate anions. Because even with that data quality, we couldn't locate 5 TPAs aldol products, because now there were also acetone and dimerized in there, we saw that, and 1 acetone and 1 water. So we see 13 TBAs, because there should be 16. So this, even the structure was lacking atoms. But we couldn't find them. They were somewhere there floating, so badly visible we couldn't locate. But we saw all the important things. And then this idea was published in Chemical Science about 7 years ago. Then what you can do with this, you can look interactions. And one we discussed already yesterday is anion-pi interaction, and in the solid state. So anion-pi interaction is really this kind of a controversial a bit. And then the idea is a possible on competing interactions with anion. So ion pairing, you know, because when we have anion, there has to be cation. And we have a coordination, it can be so that the anion coordinates to metal. We can have dipole anion interactions, of course, because if we have anion here and we have a dipole here, it's a positive charge of interaction. Or we can have a hydrogen bonding, of course. This is very well known that the hydrogen bonds to the anion. Or we can have halogen bonding. This was what I discussed yesterday. And now, finally, what we have here is this is what we look into. This is the anion-pi interaction. So we have a pi system, and we want to see if the anion is interacting with this. So there was a Ben Hay already done something like a little bit more than nearly 20 years ago, did their computational work on this kind of a thing. Lysander or the other compounds, and which proposing, okay, this kind of a species could exist. So our idea is to try to see if we can get an experimental proof for this by X-ray diffraction. And the point is, I got a student coming from a 3 months internship in my group from Germany, and we had an idea that, okay, let's study these simple salts. So we have here a highly polarized pi system, and here we have an anion is here. So here we have a chloride, here we have bromine and iodine, and here we have the same chloride and bromine. And then, of course, you can have, you have a phosphonium, and here you can have bromine. And it was a big surprise for us that actually this worked, and we got a lot of X-ray structures, although showing these. There is hydrogen bonding, of course, but now they started also we started seeing also anion-pi interactions in here in this direction. There's a strong hydrogen bonds in there. Here you can see it's really there's both hydrogen bonding and here anion-pi interactions, and the same in here. So we started a project with Markus Albrecht is his name. We did it, and this was after 3 months' work, it was published in JACS. So the student, Claudia Vessa, got a really nice paper out of 3 months' work only. And then that was the idea. We saw, like this one here, that you can see that anion can sit also on top of 2. So what we did, you can't see all of them, but then we took a PhD student, a German PhD student, do the work, has synthesized all these things, what you can see here. And we published this pile of papers on these. All in all, there were more than 110 X-ray structures. Of course, you can't see all of them. In various levels, looking for this kind of a thing. And we found out, we did analysis of which kind of a things we can see. So we can see eta 1 where it's around 1 carbon, or 2, or 3, or 4, or 5, or 6. And surprisingly, the most abundant is this eta 3 type of thing in solid state, and then it becomes eta 6, because this must not be a disturbed system. This is a very typical thing, what is there. And what we did, we actually wrote 3 big papers out of it. 1 chemical science, 1 chemical reviews, and 1 chem-com, where we published all the others between 15 and 16 for this, and coined this kind of let's say, graph out of it. So the point is that we have the receptor, and then there can be additional interactions. And then there can be lone pair, dipole interaction, hydrogen bond, cation by dipole, hydrogen bonds can be with a cation. Okay, cations have a cationic repulsion, they don't like each other, but if there's an anion, we can have anion interactions and so on. So the idea and solvents play a big role in here, and then anions have electrostatic repulsion. So all in all, point in this kind of a thing, we were able to show that really anion-pi interaction exists in solid state, it's weak, and you have to define the limits. What is the anion-pi interaction? But this is a very good example of using single crystal X-ray diffraction to extract information, data, from the structures. You can't do it from one structure, you need 100 structures in order to see the real trend. Nobody will believe if I say in one structure it's there. I said, no, I don't believe, show me more examples. So we showed that there was a 100 of them. And if I remember correctly, that was the last one. These were the examples for this. We are nicely still on time, 3 minutes. And that was end of my part. Then in the afternoon we will have the innovation workshop. I will be there also too. And now you have a chance to ask questions now, or you can then ask them after they're during the innovation and so on. And so we go until something like 5 or so, and then we will leave. But if you now have any questions, we can have a few of them. So you are completely free to ask. Yes.
Hello, sir.
Yes.
So my question is from your yesterday talk. So I
Yes.
want to get time. That's why I will ask you.
Yeah.
My first question is, if my compound is liquid
Yeah.
and I want to check that compound is single crystal exactly.
Yes.
So can I form liquid crystal from the compound any way?
Yes. Yeah. There are many ways of doing this. Depends on how liquid your crystal is, how large it is, what is the properties of this. The first thing I would look at, okay, can you protonate this? If you can protonate this by acid, I would do it and I would make a salt. Then try to crystallize, if it doesn't break down. So if it's this kind of a thing, okay. And then a great question is that, is it liquid in the normal room temperature? Does it solidify if you go down in the temperature? What happens?
Okay.
That's one thing. And then there is the ultimate thing in there, that if it's not too big and you cannot modulate the molecule at any way, then there are two possible ways of doing this. Both are rather complex, but the other one is relatively simple. So you take a solid matrix, you take a molecule with, you know, that crystallizes, and then you make a mixture of your liquid and then in this solid and try to crystallize them together. So actually the more solidifying component would like take your compound like a solvent molecule is coming to the crystal lattice. And if you can do that, then you can get the structure of your liquid thing. Or then you can use this Makoto Fujita's crystalline sponge method. You recreate a moth, and in the moth there is big enough holes that your molecule, the liquid, can go in.
Okay.
And then you just take the crystal, because its crystal is stable in that solution, and you soak your crystal in the solution where your target molecule, the liquid, is, and then you just take the crystal out, and in nice cases you have your molecule, the liquid, inside your metal organic framework, and then you can get the structure of it. Because you can have the extra structure as an empty one, or some other solvent, and you're with your molecule. So these are the ways. It can be done, but it needs really a lot of information, chemical information, about the nature of your molecule.
Okay.
But the protonation is or if you can do any other modification, chemical modification. So for example, it's an acid, make an ester out of it.
Okay.
And all these kind of things, without destroying the actual thing, because if you are looking for the core of it, what is the structure of the core, then whatever attachments you put in there will help you. For example, carbamides, if you are able to make a carbamate, carbamates are often very nicely crystalline. So there's these direct methods and indirect methods to do this. But that is, I would give you maybe a better advice if I would see your molecule and said, okay, try this and this and this and this. So that it can be done. So if your molecule is liquid, I would not give up. I would just think and try to figure out the system with it.
Okay, the another question was to
Yes.
in in host gas chemistry, so
Yeah.
we can release the gas
Yes.
from the host depending on pH of the system. So
Yeah.
what type of host molecule we can design that can release the gas according to pH?
Okay, thinking. Quite probably it would be some amine or something like that which is sensitive to pH, because it means that the microcycle itself has to be sensitive. It's not the guest, it's the host which has to be able to open in the highest pH. So probably that would be something which would say that in the native state it will encapsulate your guest molecule, but when in water, cyclodic streams are works something like this. They are soluble, water soluble, and they can trap something. But then the idea that you should modulate the cyclodic stream so that you will have some groups in there, amines or whatever, which would be then being protonated depending on the temperature. Let's say you want to go down in the pH. So you add acid, the acid protonates the amino groups, and then you will have some kind of additional push out the guest from there. But then also it could also be happening. I would study that first, not just a plain neutral microcycle with water soluble and your gas, the host is complex, and then just going down in the pH, because the pH itself changes the behavior of these things. So it might be so that it's happy inside in some pH, and then in the lower pH or so, it wants to come out. But it has to be tested. So there are many ways of doing that, but it's the simplest way to do it. Just put everything in water, have a water-soluble host complex, and then just adjust the pH in both directions. But of course, if you want to go to more the acidic side, titrate and see if it still stays there. And this will be easily done in NMR. So if you do an NMR, you show the gas is inside, and then when you start adding acid, you see if it comes out or not. That's the case.
Thank you.
Okay, welcome. Very good questions. There.
So according to our traditional electrostatic understanding,
Yes.
we heard about the pi-pi stacking or the cation pi
Yes.
interaction.
Yes. Yes.
I mean, I'm not getting what is fundamentally driving this anion pi interaction.
Very good question. Yes. So the idea is that the fundamental thing is that you need extremely polarized pi system, and it's done with the fluorine atoms. So the fluorine atoms will make the carbon atoms electrophilic. So they have what you can consider like a little bit like a positive charge type of a thing in there. And then the anion has a negative charge. So that's the idea. So the electron cloud in this let's say pentafluorobenzene rings is electron deficient, and then you have an anion which is electron rich. That's the idea. That's the driving force.
So you will always need something.
Yes, absolutely. With the benzene it doesn't work. So you need very strongly pulling electron to this, because carbon doesn't want to be nucleophilic. So you really need a pi system, you really need a strong pull. And in this case we studied, but it went very fast. We had many different types of fluorine atoms. We had 1 fluorine, 2 fluorines, 3 fluorines, 4 fluorines, and so on. But the strongest is, of course, 6, a pentafluoride, hexafluorobenzene. But then you can't make anything out of it because it's a molecule itself. So we used a lot of this. Yeah.
Some kind of quadruple interaction.
Yes, this is the idea. It's a Coulomb-based or whatever, a little bit like electrostatic or charge transfer type of interaction it is. But it's weak, it's quite weak. In solution, normally you don't see it. So they will be, because an ion pair, in a solution it will open. It's so weak. Cation pi is much stronger. Okay?
Good afternoon, sir.
Yeah.
So my question is, if I take an example of naphthalene, it's
Yes.
a volatile compound.
Yes.
And it always stays in a this one, solid state. And
Yes.
if I keep it in the room temperature, it volatilizes out. So
Yes.
similarly, if I take a gas and put it under very high pressure and
Yes.
convert it into a solid,
Yes.
is it possible to let that solidified gas compound undergo crystallography and diffraction?
Yes, yes, it is.
So how
You can do it, but the point is that it requires a precious cell. So it needs a certain idea, because the point is that you have to keep, if you push gas inside, let's say, a MOF structure, you have to keep it there, because if you take it out, you push it in the high pressure, and you take out the crystal, the gas will go out. But if you do it, there is this kind of a devices called cast chambers, where you actually you can put the crystal in there, you can pressurize that with the gas. It's a single crystal, and then you pressurize this, and then you put some light, I think 80 bars or so pressure, and then you do an X-ray on it. So that has been done for carbon dioxide by my colleague, and it's done. It's a relatively simple technique, and it can be done with the normal diffractometer. So it is possible, but it needs that if you want to have a gas inside or this kind of a thing, the difficulty is that you need the high pressure for this, and then you have to protect. It has to be on the same pressure all the time, because otherwise it will go off. But it's possible.
And is that possible with the inner gases?
Yes, of course. Yes. Like what we were doing, we put the xenon inside the cage. We actually never managed to crystallize this, but it can be done. It doesn't matter what it is. So the only thing is that you can get it organized inside there. They have to be ordered, and then they have to stay there the whole measurement. But it doesn't count what is the gas. It can be neon, krypton, xenon, whatever. It can be a noble gas, any kind of a gas. But the point in there is that based on X-ray diffraction, it has to be ordered. So the gas has always to be sit in the same position, and then you see it. And that's the complication. But it can be done, yes.
So why that orderness is needed? Why
Because the point, it doesn't diffract if there is no order. This is where what I was teaching you in the beginning. So also the gas has to be ordered. So all the atoms in this crystal have to be ordered, because if there is an ordered structure, let's consider a MOF, and then you have any molecule of gas which is not ordered, then you don't see it. Because diffraction happens only when there's order, and that's the idea. So that's the tricky. That's why the crystalline sponge method is a very genius invention, that it tries to organize the coming gas liquid always in the same place, in the same orientation. And even that is not a trivial technique. Gases are even more difficult. Consider that you have a monoatomic gas. There has to be a pocket inside the crystal, a cavity where it goes. If that's the case, that's there. It can be, in principle and theoretically speaking, it can be done, but it needs the order.
Thank you so much.
Okay.
Good afternoon, sir.
Yeah, well,
First of my one question is, how do we decide that whether the contacts, not the bonds, but the non-bonding interactions are because of, not because of just the packing that the atoms are closer, and actually there is the interaction.
yes,
So how do we know that?
that is real.
Yes.
Yeah. Okay, and very good question again. Because the point is, by nature, all the atoms, or in this, I showed the demo structure what we had, it was close packed. And then the idea is there that the molecules can be very close to each other. They can really be like this without no interaction. Because the point in there, then we call so-called packing forces. So the actual, it's like a big pressure from all the other molecules will force it to be in there, even without interactions. So if it's something which is completely unknown, let's like that, we can do computational, quantum computational calculation to see if there is really any interaction, real interaction between things, or is there not of this. So you're absolutely correct in that sense that only the closeness of the atoms in the solid state doesn't mean that there is an interaction. So in our case, we always try to show this also in solution. like I showed yesterday, that we can see, we can run on NMR, okay, we have these components in there, so then it's the real interaction, and then you just crystallize it. But it can be also so that in solution you don't see any interaction, but you see that in solid state. Argentophilic, so silver-silver interactions are a very good example of this. They are very difficult to see in solution, with the normal means, but in solid state you see them, and there it's really this kind of a thing. So you have to do additional studies in order to confirm that it's a real interaction, not just hacking. Because you can always say, okay, this comes from hacking. But you have to be very careful. It's a very good notation, yes.
And another thing is that you showed the tetrahedral arrangement
Yes.
self-assembly.
Yes.
That is in solution.
Yes.
So when you crystallize it, is the self-assembly, how do we know that that self-assembly formed in the solution and it's not because of the because of the crystalline elements when you made the crystal that happened? Like how do
Because we see this whole assembly also in solution by NMR and by mass spec. So there is additional information. So as I told you, in many cases, X-ray diffraction itself is not a proof what happens in solution. Because it might be the idea, as you pointed out, that okay, it's completely scrambled in solution, it only forms when it's in the solid state. But no, this forms first and then crystallizes. And there is a proof, NMR and all the others. We can show that that's the idea. And I show very briefly the phosphorus NMR for this. And we already, because it has to be inside, because the phosphorus peak in the solution is in a different position. So that's the idea.
And on the reverse, like how do we ensure that the crystals, while we are making the crystal, the self-assembly is not disturbed? The self-assembly formed because of the solution, like hydrophobic forces or something.
Yeah.
So how do we ensure that when we remove the driving force of the solution,
Yeah, that it doesn't break down.
that it remains in there?
Yeah, the point, normally it happens so that, because the point, this happens from water.
Yeah.
So in this X-ray structure, there is a lot of water in the crystal structure, which is not shown. So of course we don't show there's cations. This is anionic, there's a lot of cations and water. It is like surrounded with water. So the actual idea, it's in the X-ray structure, it's not only the tetrahedron, there are many other things which keeps it intact. So it's like surrounded by a water bubble. And then these are hydrogen bonded to the next one and so on and so on. So we are sure that nothing happens to it. It's like contained in the crystal.
What is the technique to ensure that the water remains like during making the crystal?
Yeah, it comes by itself. There is no technique. It just takes it with. We can't know it beforehand. We know only when we have the structure how much water is there. But we can't say water go in. We can't do this. We just do it and then see afterwards. That's the idea. No control.
Thanks.
And then,
Good afternoon, sir.
yeah.
Sir, I am having a curiosity that you
Yeah.
showed the catenons.
Yes.
The catenons having an interlocked.
Yes. Yes.
They are interlocked
Yes.
yes.
Yes. Yes.
So, what makes them interlocked and how the orderedness is maintained by the other such catenons?
So this is a very good question. So the point, in order to make the catenon, you have two things. So first, there has to be a cycle. Normally that is there. So two components forms a cycle. But then there is a third component, the same component, which goes like halfway of this, and it goes like that. And then the fourth part comes from there. So it's like you take four halves, you can do it yourself. Make first a cycle, and then put the third component through it, and then clock it from that side. This is how it works. But what it means is that the components have to interact. So this thing has to interact so that the other component can be like this. So there is interaction. It is pi-pi, it's metal coordination, any other, like in this case what I was showing, it was a pi-pi interaction. So two things went close by to each other by this. So there has to be a force interaction between this component. And then when the interaction is there, then the closing happens. That's how it works.
We have to take the first the long chains, and then we have to interlock that by some interactions.
The long chains are really bad because the long chains are, if you speak about the alkyl long chain, this is really very difficult thing because there is no functionality. So let's say the force of how the long chains will interact with each other is very weak. So we need stronger forces for this. So this is really like hydrogen bonding. Metal coordination is one which has actually started the whole thing. So you make this kind of a cross complex and then you just close it. And some of these things like these there is the knot or the other is formed by themselves. You don't have to think about these things, you just mix up the components and it happens. But there has to be interaction. This is the thing.
Okay, thank you. Sir.
Okay.
Any more questions?
One more, yes.
Dr.
Final
Sir,
question, yes.
Today you mentioned that the molecular cages,
Yes.
if you have a metal atom,
Yes.
which allows it to open up.
Yes,
So yesterday in the lecture you were showing the halogen bonding capsules.
yes.
What do they need to like open up and capture something?
That is also a very good question. We never saw the halogen bond, the I plus capsules to be open. Because they form 3 center 4 electron bond, so it's like a one bond. It's not the coordinated bond what we have. Let's say we have a tetrahedral metal cation and there are 4 ligands. One of the ligands can take off and return back. But in our case, if that happens, it breaks down the whole thing. So we never saw this in the I plus systems because it has quite a lot of covalent type nature in there, so it's not as reversible as the normal metal coordination. And that's why we can't do it reversed, because there's a question that can you reverse it? But we can't. So it's when we get it, it's there. And then it just breaks down by itself, but we can't do the exchange.
So we cannot like put some molecules inside the capsule.
Yes, we can, but it has to go, yes, we can, but it has to go from the window. So that's the idea, because in these, you know the box, what I showed you, it can encapsulate C60, but it has to open. But because now the silver one or the iodine bond capsules can't open, there has to be a window. So it goes from the window. And we have had some studies for this, but it's very complicated to see them inside. That's the idea. Okay, thank you. That was the final, our chair said that was the final question, so I think that we are happy with this, and it means that all the lecturing is now done. We will now have a break until 2 o'clock and then go on with the innovation procedure, and let's see how it goes. Okay, thanks a lot. That's it.